doing last time was working on modern. There won't be a homework or anything if you're wondering about that this week. I'll make something up this weekend. It'll probably be something on binding and on the liquid drop model and on this stuff in modern that we're reviewing. So when we left last time, we were reviewing the 1D particle in box. So I'll remind you where we were at from last class. We had done a symmetric box, asymmetric box I should say, where it went 0 to L. And we had went through just the basic ideas of applying boundary conditions to the Schrodinger equation, all stuff that you should have seen previously. And we had found the wave number K. And then because it was a free particle, we were able to calculate its momentum and stick it into p squared over 2n, assuming what? What's the requirement for that formula to be true? Non-relativistic. So assuming it's non-relativistic, which is actually a very good assumption for these things because you have nuclear levels on the order of MeVs and you have particles on the order of 938, 940 MeV. So it fits that very well. Then you put that in and we got this formula. And I didn't like that, although there's nothing wrong with this formula. I find that it's better if you go ahead and do a little bit more manipulation to it. So I had put in h over 2 pi, and I was canceling this when we ran out of time. So let's start right back there. So I had put in this 2 pi, which I'd squared and multiplied by the 2, and I got 8 pi squared. That cancels the pi squared on top. And I had ml squared. And there's nothing wrong again about stopping here. But it does require you to remember the mass off your head. But what we do is multiply the top and bottom by c squared. What that enables me to do is to take the c times the h and make that hc. Remember, that's a very useful thing to do in any problem that involves Planck's constant. Yeah.
Is there supposed to be an n squared on the top?
I'm sorry?
Is there supposed to be n squared on the top?
Yeah, I haven't finished. That's where I stopped. There's still supposed to be an n squared, but that's when it said time ran out and I didn't get the n squared. So the c goes with the h and you get an hc. So you got the 1240 MeV Fermis. The mc squared, remember we're talking about non-relativity, so this mass is the rest mass energy. So that's E naught of whatever the particle is. So the rest energy of the particle, you can see where I stopped. I didn't even finish writing particle last class.
Just arguing based on the laws of classical physics. So positive will repel positive, and negative will attract positive. So effectively, each of these charge will feel a force in this direction. Classical physics at work. So an electric field has the tendency to displace the charges from their center of oscillation. So that is what I expect based on classical physics. Now, so what really happens? So in this system, this is a quantum system. So classically, I see that. Right. But is this really the case? Is the energy modified? Yes or no? How much is modified? Can I solve the problem? Well, turns out that this problem can be solved exactly. Is again one of the few problems that can be solved exactly. Now, in order to understand the problem, then we have to amend our original Hamiltonian with a real Hamiltonian in this case. So before we didn't have an electric field, and that is Hamiltonian. Now, in addition to the original Hamiltonian term, we have a new term that should describe the interaction of a charge with an electric field. Again, so here we come to the theory of electricity. Now, every time there is an electric field, so quite generally, electromagnetism or theory of electricity tells us that this electric field originates from some electric potential. So the general formula is the following one, minus gradient of the potential. let me call the electric potential like this.
27.
What happened to these chairs?
27. Asking the chapter asked, and I think answered, what's the probability of finding in gas atoms all in, say, the left half of a container. Okay, and how do you figure that?
It's like it's like a two-body system where you want all the particles on one side, so kind of like a two Einstein solid in contact for all the energies on one side.
Okay. Basically, it's like an Einstein with Q equals, no, that's more like a two-state system. Basically, you want the probability of finding the system in the all same configuration. Basically, a macro state. Yeah, what's the probability of the macro state say all in the down position, given all the possibilities for, well, what's the multiplicity?
It'd be 10. It'd be n factorial over n factorial, so base 1. It's only one way to have them all.
Multiplicity.
Okay. We want to look at this particular contour integral close. J, which I've defined here as a contour integral, some function of z divided by sine of pi z. Now, for this to work, this function z has to be well behaved at infinity. In other words, out near z equal infinity, f of z has to go to 0 at least as fast as 1 over z. Okay. We also require that f of z have isolated singularities, which isn't a big issue, but we don't have any that aren't, that we've dealt with. Now, we know from looking at the sine of pi z, we know it's zeros. Anytime z is an integer, I have the sine of 1 pi, 2 pi, 3 pi, or 0, or minus 1 pi. So at every integer value, I have a singularity, which is good for us. Now we're going to choose a contour to do this integral. We're going to choose a contour that very skinny and totally circles the real axis. Let me try to draw it. We're going to choose a contour. You get all these singular points. So our contour is really skinny and totally enclosed the real axis. Now, I need to evaluate all these residues. So, I start doing it. This integral will be 2 pi I times the sum of the residues. there's an infinite number of them, minus infinity, infinity. The top help you evaluate it at these integer values. And we have to take the derivative of that sign, get a residue. The derivative of the sign is going to be a cosine, and I have to pull out a pi. So over here, here's my pi pulled out, and I have the cosine of n pi, which is minus 1 to the n. So look at what that says. I now have a sum over whatever this other function was, evaluated at every integer value. I've also picked up a minus 1 to the n to make it an alternating series, and I have a constant pi that can factor out. But that doesn't seem all that.
Okay, I think that means everybody is here. So, first off, did you guys see where to find your first lab reports? Okay, so in these references, there's a couple of problems. There's some really good things too. They're numbered. That's appropriate. But each one of these has an HTTP address, but it doesn't have who the publisher is. Is this a book or is this only an online periodical? And how do I get to it? So this one, the Leonard Kramer and John L. Goodman, Ionospheric Instability in the Journal of Spacecraft and Rockets, is correct. It tells me who the authors are, what journal it came from, what volume number and year and pages, and then it also has the document identifier. That is correct. There are examples in the Phys Review style of how you're supposed to do it. You need to do it that way. And no, I'm not writing it down here right now how to do it because I want you to go look it up so it sticks in your brain. Does that make a little more sense on the references as to what you're supposed to have? Does anybody have any questions on the references?
You're signing like a government website or something.
If you're,
I didn't see a BizRev styles or something like that, but when I was looking at like tables and information from government websites.
if you are getting something from a website, and there are websites that are reasonable resources, the National Nuclear Depository information, there is information that you can go get on the web. Then, yes, you do put, if you know the author, you put the author and the organization that hosts the website, and then you do put the web URL and the date of the session.